Welcome to the third Mathematics Olympiad training video for juniors with Professor Pile. Remember to buy your copy of the Olympiad training manual today.
Good afternoon, learners. And once again, welcome to this session in which we discuss problems which appeared in previous South African Maths Olympiad Junior Round 2 problems, Round 2 papers. And today we are going to tackle the problems in 2021. Last week we did 2019 and we stopped at the last question. I go to 2021 with good reason. I can explain that to you later. And we have sent out the question paper for you to look at a few days ago. I trust that you have tried those problems, because if you have not tried, well, as usual, I repeat this, there is no point in looking at an answer even before you know the question. You can learn absolutely nothing from that. Okay, I want to repeat the house rules. The rules are, please keep your microphones off, mute them. It appears in the bottom left-hand corner of your screen. Sometimes people don't follow that and they disturb everybody. We don't want to hear sounds coming from one particular source. We have a very large number of people who are all listening to what is going on, and we don't want that to happen. Also, the second house rule, the chat column, please don't abuse it. I was looking at the chat column and I observed that there were some people who are making themselves nuisances. And I would reserve the right to take them out of this class. All right, and if that happens, again, I will do exactly the same thing. Use the chat column to ask questions, not to make any wise cracks and wise comments. So with those few remarks, I want to once again welcome all of you, and I hope you enjoy the problems that we are going to do today. Mathematics is a very beautiful subject, especially if you see the elegance of some of the solutions. And it makes you think, and when you see sometimes the sheer ingenuity of people who propose the solutions, then you would appreciate it very much more. So let's go on to the 2021 paper, round 2. This is actually session 3. All right. Okay, so let's go straight to the first question. The first few questions, I'm going to go through them very quickly because many of them are quite trivial. I've got the answer here so that you can go and look at it at some other time. This is a simple subtraction sum. Okay, problem 2. Okay, let's have a quick look at this. 4a equals b. b minus a is 33. What is the value of a? It means wherever b is, you got b in terms of a. When b is equal to 4a, what this means is that the b is in terms of a. So wherever b is, you can replace it with a, and so therefore b disappears. So as we can see, this b here is replaced with 4a, and you get that. And then now you have a single equation, 3a equals 33, and therefore a is equal to 11. The next problem is a geometry problem. And you have here in this diagram, what is the value of x in the diagram? And you have 26 degrees here and 130 degrees here, and you want to know what this angle here is. This is one of those problems where you have to draw a construction. It can't be solved as it stands because the information you have does not allow you to do it without any further construction. There is a construction here. It's quite a common one in problems like this. Through this point here, you draw a line which is parallel to these two lines. All right. When you do that, then what happens is that you will see, you can calculate the x now is divided into two pieces. One of them is that, and you can see that this angle is equal to, this is z, these are lines are parallel, so that angle is 26, whereas this angle here, this is 130, these two lines are parallel, and this other angle at x is a co-interior angle. So 130 degrees, when it's added to this, you're going to get 180 degrees. So this angle here will be 50. So x is equal to 50 plus 26, and that gives you that x is equal to 76 degrees. So this was a problem where you have to use a construction to solve it. Okay. Quite clever. If you didn't do that, then you would have a problem. There is some people might have done it in another way. What they would have probably done is, instead of drawing a parallel line, you could have extended this line and extended that line. Right? And then you will see that you can extend to both of them to meet at a certain place. And when that happens, you will see that you still got these parallel lines, and these are now become alternate angles, and this becomes 26 degrees. So there is your Z. And this angle here, you can see by the exterior angle theorem, this is 130 degrees, and this 26. And this angle plus this angle is equal to that angle. This is what I call the flag theorem. Let me see a flag. Then the two angles there is equal to the extended angle. These two angles, the sum of these two angles is equal to the extended angle. And here you have the sum of these two angles is equal to the extended angle. So this angle is 104 degrees. 14 plus 26 is 130. And this is a straight line. So you subtract this one from 180 degrees, 180 minus 104. Once again, you get 76 degrees, as we proved earlier. All right, so there are two possible constructions there. Maybe there are others, but both of them lead to the same answer. Okay, the next problem. This solid here shown is a 3 centimeter by 3 centimeter by 3 centimeter cube. So you got all the sides are 3 centimeters, and you can see these cubes must all be equal to 1 centimeter for that to happen. These must be 1, the total is 3. So each cube is 1 centimeter by 1 centimeter by 1 centimeter. Okay, and a hole is drilled through the center. And the question is, what is the volume in cubic centimeters of this new solid? Okay. Now to do that, I suggest that we cut them into 3 slices. you have the top slice, and there's a bottom one, and there's a middle one. And count how many cubes there are in each slice. All right, in the top slice, you have 8, as you can see, 3, 6, 8. In the middle one, you have cubes only at the corners, at this corner, that corner, that corner. So the middle one has got only 4 of them. And the bottom one, the hole goes right through. So this bottom one will be the same as the top. So you've got 8 plus 4 plus 8 cubes altogether. So you have 20 cubes altogether. And each cube is 1 cubic centimeter, because it's all 1 by 1. Each cube has volume 1 cc, cubic centimeters, because it's 3 by 3. So you got, this is 1 here, 1 here, and 1 here. And the volume of a cube is length times breadth times height. So this is actually equal to 1 times 1 times 1, all ones. So it's 1 cubic centimeter. So there are 20 cubes. So the answer is, each one, its volume is 20 cc's. Sometimes you write this as centimeter cubed, like that, cubic centimeter. But that's the answer. Go on to problem 5. Problem 5 says that each of the 10 paths shown is 1 meter long. So where are the 10 paths here? Let's have a look. You can count them. So you got 1, 2, okay, let's count this. 1, 2 on the edge there, 3, 4, 5, 6, 7, 8, and there are 2 in between. Okay, if you went right around the boundary, there are 8, there are 2 in between, so there are 10 parts. So we've identified the 10 parts. An ant walks along from parts A to B, from here to here, without going along any path more than once. Okay. So the question is, what is the length in meters of the longest possible route? The ant starts from here and it ends here. 10 paths altogether. Now, obviously, the ant will take one of these 2, but it cannot take both. It starts walking, it cannot take this one back here because it's going to be. So one path it has to abandon. And likewise, when it comes towards B, again, it can come to B only through one possible path. So 2 paths are eliminated. There are 10 paths altogether. So the maximum you can have, the maximum length, is 8. And that's maximum, because and that will mean that one of these 2 paths is missing, but you have to use all the others. And it is possible to construct a path which uses all the others, right? I'll show you which one it is. There it is. So you can see what happens here is that you come down here, go up here, like this. There's your arrows. So it uses every possible path apart from that one, and therefore that's a path which is 8 meters long. Now, you might have tried a path which, you might have come to 7 or 6 or whatever, right? And you might think it's the largest possible path, but you always search for more. But once you come to 8, now you have to ask yourself, why can't it be 9 or why can't it be 10? And the answer is you have to miss 2 paths when you are getting, when you are going from A to B. So the maximum could be 8. Okay, so that is why we have to prove that the cannot exceed 8. The next problem says the following: if the three numbers along each diagonal are added, the average of these sums is 25. Determine the value of x. So you got a kind of like a Ferris wheel here, and you got these numbers 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 vertices, and there's a middle number here. What are they saying? So along each diagonal, you got 3 numbers. And if you take all these diagonals, how many such diagonals are there? There's a diagonal at 1, finishes at 8. Diagonal at 2, finishes at 7. Diagonal at 3, finishes at 6. And diagonal at 4, finishes at 5. So there are only 4 diagonals. So let's remember that. 4 diagonals. Therefore, there are 4 numbers. Let me go to the next page. I think I've actually created some space. Yeah, I have. So you got 4 diagonals. And they take these 4 sums. The one with 1 has got 1 plus x plus 8. The one with 2 has got 2 plus x plus 7. And the one with 3 plus x plus 6. And 4 plus x plus 5. So these 4 sums. And it is given that the average of these 4 sums is something. It's 25. The average of these 4 sums is 25. So in other words, if I add all these and divide by 4, I'm going to get 25. That is how you calculate averages. You add all the numbers, divide by 4, and the answer is this average. And when you add all these numbers, 1, 2, 3, 4, 5, 6, 7, 8, you'll get 36. But the x occurs 4 times. X plus x plus x plus x. So there you have an equation. And as we've seen many times, once you have an equation, you can solve. Multiply by 4 on both sides. 4 times 25 is 100. Bring all the x's to one side. And 100 minus 36, that is 64. 4x is 64. 4 times x is 64. So x must be 16. 64 divided by 4. Okay, so this is a problem of average. Remember, the average means you add up all the numbers and divide by the number of numbers. A very important fact about averages is that the average multiplied by the number of numbers is equal to the sum. This is used very often. The sum of the numbers is equal to the average times the number of numbers. This is what it is. The average, the sum is equal to the average times 4, 25 times 4. Okay, that's a very useful and important fact to remember whenever you're working with averages. Problem 7 says, I want to write a list of consecutive positive numbers starting with 1. The list must contain at least 3 square numbers and 3 cube numbers. What is the smallest number of integers that could be in my list? So I'm writing consecutive numbers. And it must contain at least 3 square numbers and 3 cube numbers. So let's try writing these numbers down. 1 is a nice number to start with because it is a square. 1 times 1 is also a cube. 1 times 1 times 1. Okay, so we can start with the 1. Then it's consecutive. The next one will be 2. Next one will be 3, 4. Okay, now you've got a square number, which is 4 in the set, and I've got 1 cube number, but I need to have 3 square numbers and 3 cube numbers. All right, now if you want 3 cube numbers, let's just look at, we've got 1 cubed, and you have to have another cube. The next cube will evidently be 2 cubed. And 2 cubed is 2 times 2 times 2, which is 8. So now you need to have 3 cubes. So to do that, you need to include the next one, which is 3 cubed. It's 27. So you have to include 27. Now this is certainly the smallest number of numbers that has 3 cubes, because it contains 1 cube, 2 cubed, and 3 cubed. You can't have anything smaller than that. And does it contain 3 square numbers? Well, actually, there are lots of square numbers. You've got 1 and 4, 9 and 16 and so on. There are lots of square numbers. So it's got at least 3 square numbers. It's got more than 3 square numbers. And it's got at least 3 cube numbers. Of course, here, if you want it to be the smallest, you need to have exactly 3 cube numbers. You don't want it to have anything more than that. So how many numbers are on this list? What could be the smallest number of integers in the list? The number of integers in this list is 27. Right? How many numbers are in the list? There are 27. Okay, so that takes us to the next problem. A rectangular sheet of paper has dimensions 10 centimeter by 15 centimeters. And we don't see a rectangular sheet of paper here, but it was a rectangle, it seems. So you got 10 down here and 15 this way. So that's the dimensions. And from this sheet, 12 1 centimeter by 1 centimeter squares are cut out. Okay, so these are cut out, and these are 1 centimeter by 1 centimeter. So you got lots of squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 1 centimeter squares which have been cut out. Okay, what is the perimeter of the resulting shape in centimeters? Now, the perimeter means if you go right round, come down this dip, go to do that, go up, go like this. So the perimeter means you're going all around the boundary. And if you start like this and go here, you say, well, I don't know how many there are here. It's unknown. This is 1, this is 1, this is 1. And again, this is unknown, 1, 1, 1. If you do it like that, you're not going to get anywhere. So how do we really solve this problem? Okay, the answer is that you see what the original perimeter was. Take the perimeter of the full rectangle. Suppose I connect to this. And so on. Now, what is the perimeter of the rectangle? So it is 10 by 15. So it's 2 into length plus breadth. If you don't like to use formulae, you can put 10 plus 15 plus 10 plus 15. You come to the same answer, and that gives you 50. Because 10 plus 15 is 25. And each one is added twice. So that's the perimeter of the rectangle. But now what happens is that we didn't need the perimeter of the rectangle. The rectangle has all these outside edges here, but it also has these inside, these 3. So you got 3 here, but we've counted 1 extra piece there that wasn't there. So what we've got is, so in other words, I'm actually counting this one here. But there are two more which I did not count here. This and this. So if I take that and say I'm counting that one, there are another two which I didn't count here. This is counted, but this is not counted. Okay, so how many are missing here? There are two here, there's another two here, and like that, at each square, there are two extra sides. So the perimeter that we want of the figure is equal to 50. That's the perimeter of the rectangle. Plus, at each square, you got two extra sides which we didn't count. So there are 12 such squares. So it's plus 2 times 12. At each of these squares, right? So we have to count that one and that one. That one and that one, and so on. So that gives you 24 plus 50, and that is 74. The answer is in centimeters. Okay, because the units are given in centimeters. So that's the perimeter of the shape. Okay, you have to use you have to think about it and see how can you do it in an easy way. So you really calculate the perimeter of the rectangle. Then you ask yourself, how much more do I need to count? And that's where the plus comes in. And you will see that you need to count, 24 vertical lines, which were missing. In this case, they were vertical lines. And you'll have to add them. Okay. Problem 9. The sum of 5 consecutive positive integers starting with n is a perfect square. What is the smallest possible value of n? Okay, so you got 5 consecutive numbers starting with n, and we want to know when you add them, they're consecutive, right? When you add them, it is a perfect square, a square number. So let's see the possibilities. You could have had 1, 2, 3, 4, 5. When you add this, can I add it? You get 15, and that's not a square. All right, so we ignore that. Okay, the next one, we want the smallest possible value of n. So we start with small values of n, like 2. We finished with 1, it doesn't work. 2 plus 3 plus 4 plus 5 plus 6 is actually equal to 20. And that is not a perfect square. But if you try 2 plus, and the next one will be 3 plus 4 plus 5 plus 6 plus 7. Why do I? Plus 6 plus 7. I'm sorry, it's 3 plus 4. That gives you 12, 18, that gives you 25. And that's a perfect square. And that is the smallest. We've started with n equals, n is starting with n. So n is this. This is n is equal to 1. N equals 2. N equals 3 gives you the answer. So the answer is 3. The question is, what is the smallest possible value of n? So n is the first number in this thing. So the answer is 3. Okay, it turns out that you can get the answer by trial and error. But it would have been very uncomfortable if the actual answer was at some large number, like say n is equal to 56 or something. You're not going to go through this process like this, all right? And you keep going on and on and on, you never come to a perfect square. It could have been like that. Fortunately, this thing ended after the third step. So, we were in a bit of luck here because we were doing it by trial and error. We were trying out 1, 2, and 3, and it worked. But in mathematics, often you cannot use trial and error. Like for instance, if the answer was at 56, trial and error would not get you to the answer. So we have to think of some other way. I want to point out here 15. It's always 5 numbers, and you notice this is 5 times 3, 5 times 4, 5 times 5, and 3, 4, and 5 are the middle numbers in these. So when you add up all these numbers, you really have the number of numbers times the middle number. It's an interesting thing, but you'll only have a middle number if you've got an odd number of numbers. If you had an even number of numbers, there's no middle number, right? Like 2 and 3, now there's no middle number if you just had 2 plus 3. But with the odd number, there is a middle number. So it always works out like this. The sum of all the numbers is the number of numbers times the middle number. See? When I say always, that is provided these numbers, they need not be consecutive. They could have a fixed common difference. Some of you might have learned this. Like for instance, if I had 4 and 7 and 10 and 13, I keep adding the same thing, but I keep adding 3, right? And I got 7 here, 7 numbers. And if you're adding this, all these numbers, it will be equal to the sum of these numbers is equal to, how many have you got? 1, 2, 3, 4, 5, 6, 7. The middle number is 13. So it's 7 times 13, and that is 91. If you try actually adding these numbers, hopefully you'll get 91. So it's a nice formula. If you've got what we call an arithmetic sequence, which means you've got a common difference, you've got an odd number of terms, the sum of all those is equal to the number of terms times the middle number. Be careful, don't use this all the time. It's only when you have an odd number of terms, A, and B, when you've got a common difference, when you're adding the same number all the time to get to the next one. Only in that case, you can use this principle. The other way of doing this thing here is you could have used mathematics because they say that the smallest number is n. So let's see what happens when you do that. So if you start to do the smallest number is n, then you're adding n plus 1, consecutive numbers. The next one, n plus 2. The next one, n plus 3. The next one, n plus 4. Right, so you got 5 consecutive numbers, you're adding them, and the answer is a perfect square. All right, but let's just add them and see what happens first. This is 5n, n plus n, there are 5 of them. And when you're adding 1 plus 2 plus 3 plus 4, you get 5n plus 10. So that's what this is. And that is equal to 5 into n plus 2. 5 comes out as a common factor. And observe, this is 5 times the middle number, you see? This is where it's coming from. You got the 5 numbers here, and the middle number is n plus 2. So I've just given you a proof as to why this is 5 times the middle number. All right, so you want this to be a perfect square. It's a square number. And you want the smallest. Yes, the way to do this is this one here must be It has to be 5. That'll give you a number, square number, 5 times 5. Right? Or you could have had n plus 2 equal to 23. You could have had that too. Now, wait a minute. We have 18. N equals 18 will also work. Because 18 plus 2 is 20. 20 times 5 is 100. So there are other numbers which will work. But the smallest one, you're looking for the smallest, is 5. And that gives you n equals 3. N plus 2 is 5. N is equal to 5 minus 2. And that's exactly what we had before, that the answer is 3. So you could have done it like this, where you use mathematics and say, you want this to be a square number. You got 5 here. 5 times what is a square? It has to be 5. Oof. And therefore, you got an equation for n, and you can solve for n equals 3. But you could have had 5 times a square number, right? But I'm not going to go into that. That's how I got 18. So let's not worry too much about that. In case you asked, how did I get 18 so quickly? I just took 5 times a square number. Okay, the square number I took was 4. 5 times 4, which is 20. And n plus 2 is 20. So n will be 18. Okay, now the next one, problem 10. The first 100 natural numbers, from the first 100 natural, 1 to 100, all the multiples of 2 are removed. So you write down all the numbers from 1 to 100. And you remove the multiples of 2. So suppose, obviously, I'm not going to write down all the numbers from 1 to 100. I have to imagine. So you go all the way up, dot, 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 going up to 100. All right, the multiples of 2 are removed. In other words, 2, 4, up to 100. So how many are removed? 2, 4, 6, all the way up to 100. There are 50 of them. 2 times 1, 2 times 2, 2 times 3, 2 times 50. So you can actually count this. There are 50 of these. So at this stage here, 50 are removed. Okay, I'm here at this stage here. 50 are removed. And then all the multiples of 5 are removed. Okay, so you have 5. So the multiples of 5 are 5, 10, 15, 20, 25, and so on, all the way up to 95, 100. Multiples of 5, they end in 5 or 0. But all this collection here now, the even numbers are taken out. So in this collection, right, there are no even numbers. So let's take those. So you only got 5, 15 up to 95. So the multiples of 5, which are removed from this lot, is 5, 10, no, I'm sorry, 5, 15, 25, 35, all the way up to 95. Well, you can count this by saying that you got a 0 there. So you got to count them. The first digit counts 1, 2, 3, 4, 5, 6, 7, 8, 9. There's one more. So there are 10 of these which are removed. So, and 10 more. You might think that 100 divided by 5 is 20, but You can't subtract 20 because amongst the even numbers, there were 10 even numbers which were there, which were multiples of 5, 10 going all the way up to 100. So they have already been removed. So the remaining ones, there are 10 more. So there are 60 removed altogether from 100. So you had 60 which were removed. So how many are left? How many numbers are left? That's a question. That's 40. Right? Because you want to know how many are left. So the answer is 100 minus 60. 60 were taken away. You had originally 100, so therefore there are 40 left. Okay, so the next problem. All the prime numbers less than 2021 are multiplied together. What is the units digit of this product? That's quite a thing. There are lots of prime numbers less than 2021, and you're going to multiply all these. So it says all the prime numbers less than 2021 are multiplied together. Okay, so first we have to ask ourselves, what are the prime numbers less than 2021? So you're starting with the first prime number. The first prime number is 2. It's one of the most important prime numbers. I'll tell you just now why. The next one is 3. It's a prime number. 5 is the next one. And 7, 11, 13, and so on. All these going all the way up to 2021. And these are multiplied. So you have 2 times 3 times 5 times 7, 11 times 13, and so on. A lot of it. It's a huge number. You're multiplying hundreds of numbers. But the question is not what the answer is. The question is, what is the units digit? In other words, what is the last digit of this product? And the answer is quite clear. If you look at this, you see 2 times 5 is 10. So this is equal to 10 multiplied by something. We don't really care what it is because you got 3 times 7 times 11, some monstrous number. So 2 times 5 is 10, and the other number is 3 times 7, 13, and so on, 11 times 13. But it doesn't really matter what this is. Any number multiplied by 10 will end in a 0. And that's the units digit you're looking for. You want to know what is the last digit of the product? Well, you got this thing here multiplied by 10, and you all know that any number multiplied by 10, well, all you have to do is to stick a 0 at the end of that number, and that's the answer. Right? 2,137 times 10 is that. You just simply stick in a 0 at the end. That's how you multiply by 10. So that's the units digit of this product. You're multiplying them, so there's a product, and this is the units digit. Okay, so we get on to the next one. "16 jelly tots," whatever they are, they are arranged in a 4x4 square. So you got, okay, 4x4. Actually, this is more like 3x3, but because of the jelly tots, you got 4 jelly tots in each row, and 4 columns. So therefore, there are 4x4. So there are 16. You can see 4 times 4 is 16. And they are connected with toothpicks. So these things are all toothpicks. All these. So this is the diagram. But if you had, how many toothpicks would be needed for a 10 by 10 square containing 100 jelly tots? Now the question is how many toothpicks? How many toothpicks are here? You got, those are the horizontal and the vertical lines. So if you count the toothpicks, you got 1, 2, 3, 3, 3, 3, 3. So it's 12, 4 threes. Three, 3, 3, 3. And then you got the columns also, 3, 3, 3, 3, the vertical toothpicks. And that's also the same answer. So in this picture here, you got 12 plus 12, which is 24. Which is actually, if you think about it, it's 2 times. This 2 here represents, you are saying that the number of toothpicks along the horizontals is the same as the number of toothpicks along the verticals. So we don't have to add the horizontals separately from the verticals. You just add the horizontals and multiply by 2. And the horizontals we saw was 4 times 3. That's the number of toothpicks you have, because if there are four jelly tots, there are only 3 toothpicks which connect them. Right? But there are 4 such rows, so it's 4 times 3. So if you extrapolate that idea, so if you have 10 by 10, now you got, it's very much more complicated because you got a lot of toothpicks now. But if you think of this thing here, what happened was, it will be 2 times. So you work out all the horizontals. In the horizontals, in each horizontal row, if there are 10 toothpicks, 1, 2, 3, 4, 5, 6, 7, 8, 10, right? You will see that there are only 9 toothpicks, 10 jelly tots, just like as we had 3 here, 3 toothpicks for 4 jelly tots. You'll have 9 in each of those rows, but there are 10 rows, so it's 10 times 9. Very much like 4 times 3. See? So there are 10 rows, each having 9. So this is the answer. 2 times 10 times 9, which is 180. All right. And just to summarize, there are only 9, although there are 10 jelly tots, there are only 9 toothpicks in each row. That is the sort of trick in this problem. You might think it's 10. It's only 9 toothpicks, but there are 10 rows. Right? So the number of horizontal ones is 10 times 9. That's how you get that. The number of verticals is also 10 times 9. So you have to multiply 10 times 9 and double it to get this answer. We are now problem 13. As we saw, as it goes on, the problem will become a little bit more and more challenging. But in all cases, as you see here, hardly any mathematics. We're not writing equations and solving all kinds of complicated things. A lot of it is just common sense. We argue and we reason, and logically we figure out what is going on, right? We must understand the problem and working with numbers as though they are living objects, you know? And you have to understand, if you're adding, if you're multiplying, you know, you tell yourself this is what you're doing, you're adding or you're multiplying. Once you get the operations, you know, clear, and then if you got your symbols, then you go around and get equations. Now let's have a look at this problem. The positive integers. So this is important to recognize that these are integers and they are positive. So we are saying that we are looking at the integers which are 1, 2, and 3, and these are positives. We're not including 0 and -1 and -2. 0 is not positive. The smallest positive integer is 1. So these are, so x, y, and z are, they are equal to one of these. They're coming from this set here, right? Now x, y equals 10. YZ is equal to 15. ZX is equal to 6. So you got integers. You're multiplying two integers to get this. So you ask yourself, what can x and y be? In this case, you can have 1 times 10 or 10 times 1, or you could have had 2 times 5 or 5 times 2. So the x value could be various kind of things. Similarly with y, z, see, y could be, it could be 1 times 15 or 3 times 5, or 15 times 1 and 5 times 3, right? That means y is 15 or 1. X is could be any one of 3 possibilities: 1, 2, or 5. Y is 1, 3, or 5. And Z is in the similar way, it's going to be 1, 2, or 3, or 6. Right? But I want to look at these two. In fact, I could take any two. I could take even the first two. And then you say Z is a factor of 15, and Z is also a factor of 6. So now that cuts it down now. If Z is a factor of 15, Z could be 1, because 1 is a factor of 15 and 6, but the other one is 3. 3 is a factor of 15 and 6, and there are no other numbers. So Z is equal to 1 or 3 from these two. We are talking about factors here because you got whole numbers, you see. When you multiply these two and you get 10 and these are positive integers, now we can talk about factorization. Because you are multiplying these two positive integers to get 10, you can say x is a factor of 10. You can't say, like, for instance, if you had half times 6 is equal to 3, right? Half of 6 is 3. You can't say half is a factor of 3. It doesn't make any sense. You only speak about factors when you got integers. Very important fact. Please remember that. When you work with integers, then you got factors, right? And you've got common factors, and you've got LCMs, you've got HCFs, you've got those kinds of things with you when you're working with the integers, and more specifically positive integers. But if you were not told that these are integers, and you got a half times 6, we know is 3, you can't say half is a factor of 3. Right? Because you could have 1/3 times 18. I'm sorry, 1/3 of 9 is also 3. You can't say 1/3 is a factor of 3. In fact, you can take any number and say it's a factor of 3. It doesn't make any sense. But you can only do this. So that is why the positive integers are very important. Now, if Z is equal to 1, okay, let's have a look. If Z is equal to 1, then you got Y is equal to 15. Because Z is equal to 1. But now you will have that Y is a factor of 10. Because from here. But Y is a factor of 10. You see, this is how you work with positive integers. Because x times y is 10. Now 15 can't be 15 is not a factor of 10. So I've said it, if Z is equal to 1, if Z is equal to 1, you substitute Z equals 1 here, and you get Y is equal to 15. But then when you go there, you see 15 is a factor of 10, which doesn't make any sense, right? So this thing here is wrong. You can't have z equals 1. So therefore, we can now conclude, we can say hence, or the conclusion is that z must be 3. Z is forced to be 3. Okay, now if z is 3, let's see, you've got x, y, z. Z equals 3. You can put 3 here, and you get y is equal to 5. And then you put z equals 3 here, and you get x is equal to 2. Z equals 3, therefore x is equal to 2. So you got the whole lot. And you can check it out. X, y is 10. There it is. X times y is 10. Y, z is 15. 5 times 3. So this reasoning came to the correct answer. And you need to work out x plus y plus z. So all you have to do is to add up all these things. X plus y plus z, and that is 10. 2 plus 5 plus 3 is what you're looking for. So you always look at the question and answer the question. The question was not to find x or find y or find z, but you needed to find all three to get x plus y plus z. Well, generally, sometimes you need not find all three. You will see some problems like that. Okay, so we will okay, we are now at problem 14. If the pattern continues in the same way, how many shaded blocks will there be in figure 30? So you got, what is the pattern now? The pattern is, if you look at all three simultaneously, you see the pattern is you're shading the right-hand column, you're shading the bottom row, and you're shading the diagonals. Right? That diagonal, you're shading all of them. So the question is how many shaded blocks? So we need to count the number of shaded blocks. In figure 30. All right, so it means we have to see what kind of pattern is going on here, right? Just simply adding them, you can do that. If you add all these numbers, the shaded parts, you will see you got 9 here. And here, if you add the shaded parts, you got 12. And here, if you add the shaded parts, you'll have 15, I think. So in figure 1, the shaded part is 9. Figure 2 is 15, 12, 15. And your guess is, you can see this is 3 times 3. There is a pattern. This is 3 times 4. 3 times 5. There is a pattern. So they're all multiples of 3. But the other factor is 3. Now, where did 3 come from? It's 4 minus 1. This is a 4 by 4. So this is 1 less than 4. This 4 is coming from this, right? And it's 1 less than 5. And the 5 is coming from here. There are 6 rows, and 5 is 1 less than that. So if you're going to figure 30, it'll be 3 times what? Okay. The other way of looking at it is this, the what is 1 more than the figure. So it's 1 plus 2, 2 plus 2, 3 plus 2. So the second number is 2 more than the figure. So it's supposed to be 32. So our guess is that the answer is 96. That's our guess. And there's reasonable grounds to believe that the guess is correct because you've got a pattern. 3 times 3, 3 times 4, 3 times 5, that's the number of shade parts. Because when you count them, you've got 9, 12, and 15. Straight away, you can see there, works out like this. And then figure 1 has got a 3, figure 2 has got a 4, figure 3 has got a 5. So figure 30, we should have 32. So it's 3 times 32. Okay, so the answer is 96. Now, you might not have worked it out like that. You could have said, well, I'm not going to actually count them. I'm going to see if there is a pattern in the way we are adding them. And I could have, if you look at just the inside squares here, there's 2 here, that plus that, 2. And then when you come down here now, there's 3, I'm sorry, 2 plus 3, 2 plus 3, don't count the bottom one, plus 4. We could have decided that this is 2 plus 3 plus 4, and you can see that's also 9. Now again, here you can just count the inside ones. That's 3. Don't count the bottom ones. There's 3. Here you count the extremes here, but don't count the bottom one. That's plus 4. Now you can count all the bottom ones. The 3 plus 4 plus 5. Likewise, this is 4 plus 5 plus 6. Right? And therefore, the 30th one, now where did 4 come from? It's 1 more than the figure. 3 is 1 more than the figure. And 2 is 1 more than the figure. So for figure 30, for figure 30, it will be 31 plus 32 plus 33. Okay, consecutive numbers, odd numbers, so it's 3 times 32, which I told you earlier on, and 3 times 32 is 96. Or if you want to add them, which is not very difficult, you can add them and get 96. So the answer, you still get the same answer if you see the pattern in a different way. Okay, and maybe there might be some other ways of getting this pattern. I'm sure people will figure out some other ways of getting to this answer. I think the first one we did is the easiest one. Just count this and check to see what the pattern looks like. All right, let's get on to the next problem. Problem 15, the diagram shows 3 identical squares of side lengths 8. So what we've got here is that all these sides are 8. All right. The top square is exactly centered over the 2 squares below it. As you can see, this is exactly centered. So that means that this part here is 4, but from here to the end, it's 4. Be careful. Okay. Yeah, so this part here will be 4. From here to here is 4, and this part is 4. Because this is center, the whole thing is 8, so therefore it's 4, 4. So this part here is 4, and the outside part here will also be 4. Okay, now the question is, determine the area of the shaded region in square centimeters. The shaded region is a pretty odd kind of a region. Now remember, where this cuts here is not the same as the center. There's a little line here. So be careful, don't think that you got a triangle here. You don't have a triangle. Right? You may have a triangle here, but you don't have a triangle. This triangle can go like that. But we don't know what the length of the small piece is. There's a small piece there. So when you try to calculate the area of this, you'll say, well, I've got the area of a triangle and the area of something else, which looks like a trapezium. It's got a small piece here, but I don't know what this thing here is, and I don't know how to calculate it. So that when you try to do it like that, you'll see that you'll come to you'll reach a blank wall. So this is one of those examples where you have to use a construction. You say, but wait a minute, the piece which has been removed is actually a rectangle. So why don't I know how to find the area of a rectangle. So let me see what's been removed. Right? So that's a rectangle. And that rectangle is removed from an entire triangle. And this is, a very respectable triangle here. Right? So to find the shaded square, all you need to do is to find the area of the large triangle and subtract from it the area of this rectangle. So that tells you how to solve the problem. Okay, so if you complete the rectangle, suddenly the solution, becomes quite obvious. So if this rectangle is now 4 there like that, and this length here is still 8, and this is 8, all the sides are 8. So the area of the triangle, area of the large triangle, so the shaded part, is equal to the area of the triangle minus the area of the rectangle. Right. The area of the triangle is that's a right angle triangle because it's a rectangle there. It's half base times height. 8 plus 4 is 12. So it's 6 times 16. Or if you want to use that as a base, you could have said 8 times 12. Get to the same answer. The area of the rectangle is 8 times 4. Length and breadth. So you subtract the rectangle, 8 times 4, and you have 64. And it's centimeters, so you have to say square centimeters. Or centimeters squared. Okay, so determine the area of the shaded region in square centimeters. That's what we just did. So we calculated the area of the triangle, which is 96, and 6 times 16 is 96, or 12 times 8. We subtracted 8 times 4, which is 32, and the answer is 64. Okay, so we just go down to the next one. The combination for a certain lock is a 4-digit number with no 2 adjacent digits the same. How many combinations are possible if the digits are 2021? So a lock has got numbers in it, 4-digit number. So in problems like this, it's always nice to draw a rectangle divided up into 4 equal parts. Right? And you're going to put 2021 in these. So you could have 0221, 1 to 1022 or whatever. But it said that no 2 adjacent digits are the same, which means you can't have 2 and 2 next to each other. So you could have, for instance, you could have 2021. Okay, that's fine. But 2201 is out. Or 1022 is out. Right? Now the question is, how many such numbers have you got? We can actually list them down. If you say, okay, suppose the first digit is 2, you can't put 2 here, but you can put 2 as the third one, and you can put the other 2 digits here. You can do that. So that gives you, you can put 0 and 1 here. So you can put 2021, or you can put 2120. Where you put 0 and 1, or you could put 10. All right. Now this is where you've got 2 in front. Can't be the second one. Or you could have 2 in front again, but it can be the fourth one. You can have, if 2 is in front, then you could have had 2 as the last one. And again, there are 2 numbers here. If you want to list them down, it's 2012 and 2102. And 2 is the last one, and these 2 are there. Or you could have had, okay, that takes care of 2 being the first one. Now, suppose 2 is the second one, the second digit, right? Now finish with the first digit. 2 can't be here. So you're going to have second and fourth, 2 can't be next to it. And again, you have 2 other numbers here. Now, this time you have 1202, or you could have had 0, 1, I'm sorry, 0, 2, 1, 2. Put 1, 0 and 0, 1. Right? Okay, and you can't have any other 2s. This is the only way you can put the 2s. You can't put them next to each other here. All right, so the answer is 6, because you can count all these and you can get the answer to be 6. But the way I would have done it is, I'll say, look here, I won't write down all these. I just ignore these. There's no need to write down all the numbers. All we need to know is how many there are in each. In here, there are 2. Here, there are 2. Here, there are 2. And that's how you get 6, because you got 3 groups of 2. So you could have argued that this thing here allows 2 numbers, because you can put 0, 1, 1, 0. This allows 2 numbers. This allows 2 numbers. So you got 3 different groups, and each one has got 2 in it. So it's 3 times 2. Instead of listing all the numbers, you can say, I got 3 types of numbers. I can have 2 blank 2, or you can have 2 blank blank 2, or you could have blank 2 blank 2. But then you could have interchanged these numbers, 0, 1, 1, 0. So there are 2 ways in which you can get such a number, which we have listed earlier on. And for each one of them like that, you got 2 ways. Then you argue. The reasoning is there are 3 groups, and each one of them has got 2 numbers. Therefore, 3 times 2 equals 6 is the total numbers you've got. There are 3 groups, and each one of them has got 2 answers. So therefore, it's 3 times 2 equals 6. So that's the logical way of getting to the answer, instead of writing down all these answers. So it could have been more complicated, then that logic then will take over. When I say more complicated, I could have had a lock. What do we call that? Some lock or whatever. Could have had 8 spaces, and they say, you know, no 2 numbers are next to each other or something like that. Then it becomes very much more complicated to count. But if you use an argument like the way I used just now, very often you can actually solve these problems much more easily. Okay, the next problem, the average of 10 scores is 80. So here, you know the number of scores and you know the average. That's very useful because if you know the average and if you know the number of scores, how do we calculate the average? You add all the scores and divide by 10 to get 80. So what we know is the sum of all 10 numbers. Is 80 times 10. Right? Because when you add that sum and divide by 10, you're going to get 80. That's how you calculate the average, because there are 10 scores. Then that immediately follows that you can multiply 80 times 10 to get to the sum of all the numbers when you add them up. Now, when the highest and the lowest are removed, now you have two numbers are removed. So then the average is 70. So when two numbers are removed, the highest and the lowest, the average is 70. So therefore the sum of these, the smallest set of numbers, which is 8, right, is 70 times 8. Those two numbers are removed. So now you've got only 8 numbers. And when you add up all those 8 numbers and divide by 8, you get 70. So the sum of those 8 numbers is 560. Now what is the average of the two scores which are removed? So now you can see quite clearly that the sum of 10 numbers is that, and the sum of 8 numbers is that. Then the sum of the removed numbers would have been 800 minus 560, which is 240. But that's the sum of the two removed numbers. So you're adding two numbers to get this. So the average, they're asking for the average of the two numbers. Of the removed numbers, and there are two of them. Must be the sum divided by the number of such numbers, and that's the answer. Question was, what is the average of the two scores which were removed? I've just calculated that. Okay, so we are using the fact that the sum of numbers is equal to the average times the number of numbers. Very, very important fact, right? So we've had at least 2 problems involving averages. So they're not the same kind of problems, but as long as you understand what you mean by average, then you write the equations down, then you should be able to solve all these problems, like the way I'm doing. Problem 18, xy, if xy minus 2y equals 10, where x and y are positive integers. Again, you got x and y are positive integers. And we saw earlier on how you deal with these things. So x is one of these numbers, 1, 2, 3, and so on. And same with the y. Y or x comes to those numbers. So as I said, amongst this set here, you have factorization, you have HCF, common factors, all that kind of stuff. What is the sum of all the possible values of x? Okay, now you got xy minus 2y equals 10. We can write that down as y into x minus 2 is 10. All right, now these are integers. Now, x minus, okay, let's look at, you can either take, the product of these two numbers is 10. So therefore, y is a factor of 10, and so is x minus 2. Now, y is 1, 2, 3, whatever. And the same with x minus 2. But if x is 1, then x minus 2 is 1 minus 2. That creates negative numbers. So let's not worry about this. X minus 2 is a factor, but rather look at y. Y is a factor of 10, and y is one of these numbers. So we can immediately write down what y is. Y is a factor of 10. What are the factors of 10? Well, the factors of 10 are 1 times 10, it's 1 and 10. Or you could have 2 and 5. Right? So you got the factors of 10. I like it like this. We put 1 and 10, immediately I write down the other factor. And put 2 and immediately write down the other factor. So there are 4 possible values for y. Now, y times x minus 2 is 10. So if y is 1, x minus 2 will then be 10, because you're multiplying these two. The product of these two is 10. Here, you're going to have 1 here. Product of these two is 10. And here, you're going to have 5. And here, you're going to have 2. Because y times x minus 2 is 10. So 1 times 10 is 10. Otherwise, you can say it's 10 divided by y. X minus 2 is 10 divided by y. 10 over 1, 10 over 10, 10 over 2, 10 over 5. But that's x minus 2. We need to find out the sum of all possible values of x. We got 4 possible values for x minus 2, which means I've got 4 possible values for x, because x minus 2, if it's equal to 10, if I bring the 2 to the other side, it will be 10 plus 2. So that'll be 12. You can do the same thing for each of these, because you're going to add 2. Bring 2 to the other side. So x minus 2 is any one of these. So x is equal to any of these plus 2. You bring 2 to the other side. So when you add 2 to each one of them, this is what you got. Now you got all the possible values for x. And the question was, what is the sum? So the sum is equal to 12 plus 3 plus 7 plus 4. The answer is 26. When you add these 4 numbers, you get 26. So that's the answer to this problem. All right, let's say again, the important thing here is that when you say y into x minus 2 equals 10, please don't ever do this when you do school mathematics. Don't say therefore y equals 1, or y equals 10, or y equals 2, or y equals 5. That'll be completely wrong, because here we are using the fact that these are positive integers. Right? We know that y is going to be one of these. But if it was not told that y is a positive integer, you could have put y equal to, for instance, I could have put y is equal to 5/7. Right? And then once you put 5/7, you can solve for x. Then you put 5/7 into x minus 2 equals 10, and go on to calculate what x is. Say 5 into x minus 2 is equal to 70, x minus 2 is equal to 14, and x is equal to 16. So there x will be equal to 16. But now these are not integers, you see. And you could put any number you like here, and you could get so many answers. But the fact that it's an integer, a positive integer, allows you to say that there are only 4 possible values for y. That's a very, very powerful statement. See, there is a positive integer. So you don't have, here you can have infinitely many values for y, because I just picked y equals 5, 7 from a hat. I could have put y equal to 112 over 793, right? And solve for x. You can put any number you like for y and you can solve for x, right? But you have lots and lots of possible values for y. But because y is a positive integer, there are only 4 possible values. So these questions which involve prime numbers, positive integers, and so on, they are not very difficult. You just have to take the different cases and go and try to solve them. Okay, so let's just clear all these drawings first. Okay, problem 19. We have problem 19 now. A fruit basket contains bananas and grapes. The ratio of bananas to grapes in the basket is 3:8. Right, I just want to stop there and let's not worry about the rest of the problem. We've got this. Bananas to grapes. Of course, when they say ratio of bananas, they mean the ratio of the number of bananas. Number. The ratio is always between 2 numbers. Is 3:8. Now, I just want to pause here. So you got a number. This is the same as saying the number of bananas over the number of grapes is equal to 3/8. Remember that. When you got a ratio is given, you can say this divided by this is that ratio. Now here is something that I want to point out. Now listen very carefully, all of you, okay? See, when you write a fraction, 3/8, there are many ways in which you can write this fraction, right? This is the simplest form. You could have said this is 6/16. If I had 6/16, I cancel the 2s, I get to that. But what I'm doing here is I'm multiplying each one of them by 2. I'll get the same answer. So I can multiply the top by 3, multiply the bottom by 3, and this will give the same thing because then you can cancel the 3s and you come back to the same answer. Right. So there are many ways in which you can write. If I multiply top by 4, get that. If I multiply top and bottom by 5. So there are many, many ways, infinitely many ways in which you can write this fraction. So what we are saying is that the number of bananas, sometimes you might say is equal to 3. And the number of grapes is 3. That will be false. Because the number of bananas is any one of 3 or 6 or 9 or 12 or 15 or anything. It's a multiple of 3. So in actual fact, the number of bananas, watch, the number of bananas is equal to 3 times x. Now here, you know, it's not equal to 3, but it's 3 times something. And the number of grapes is 8 times the same thing. So that when you put 3x over 8x, the x is cancelled, you get 3/8. Whenever you have a proportional problem, a ratio problem, please do it like this. Because you can get equations. Now I got equations. I can say number of bananas. I can say what it is equal to. But there is an unknown here. I do not say that it's equal to 3. But I say it's equal to 3 times something. But you got the same x at the bottom. So this is a very, very important fact about ratios. Because when you do it like this, you can solve a lot of problems. Okay. So if you get to I've written this problem out again. Okay, so I've got the number of bananas is equal to 3x and the number of grapes is equal to 8x. We don't know what x is. Now I say when I remove one banana, the ratio changes. So what happens? Now I got the number of bananas. I know what it is. If I remove one banana, I've got 3x minus 1 bananas because 1 is removed. I haven't done anything to the grapes. So the number of grapes still stands at 8x. So when I remove one banana, I got 3x minus 1 over the number of grapes. And now the ratio now, this new ratio, it changes to 1 over 3. And there it is, you got an equation. See, the whole idea in problem solving is to try to get equations. In here, in the proportional problems or ratio problems, there is an unknown, and the problem is to find that unknown, and you can use the information to do it. And here, to solve this, you cross multiply 3 into 3x minus 1 equals, cross multiply here, you got 8x. Right? 3 into 3x minus 1 is 9x minus 3. Expand, bring all the x's to one side, 9x minus 8x is x. Bring the 3 to the other side, x equals 3. Right? Now you don't stop there. Because the question was how many grapes are there in the basket? Right? There are no, it's not true that there are 3 grapes. The number of grapes is 8x. The number of grapes is 8x. So it's x is 3. The number of grapes is 8 times 3. That's 24. See? The number of grapes is 24. And the number of bananas was 9. Right? X is 3. So that's the answer. See, we can check it out. Because we say there are 9 bananas and 24 grapes. So bananas to grapes is 9 to 24. As you can see, it's 3 over 8. One banana is removed, so the 9 now becomes 8. Number of grapes hasn't changed. 8 over 24, as you can see, is 1 over 3. It's cancelled. Okay. So this is a very neat way of solving this by creating an equation and then solving it. Okay, I hope you remember that technique. Okay, we are now at problem number 20. A rectangle is cut into 2 regions by a single line. There's a rectangle cut into 2 regions by a single line from a corner as shown. So from a corner, you draw a line to the other side. We don't know what the length and the breadth of the rectangle is, and what that is, but we are just told there's a line which is drawn. They say the area of the 2 regions are in the ratio 1:5. So the ratio of A is to, there are 2 regions, that, and the ratio of the 2 regions is 1:5. If A plus B is 48, okay, now that's very nice because you know the breadth of the rectangle. Okay, that's A plus B. It's 48. Determine the length of A. Okay, so I seem to have created some space here. All right, so we know this whole length here is 48, A plus B. And the ratio of this to this is 1:5. So there are two unknowns in this. Let's give a name to these unknowns. Suppose the area here is A. We are saying the areas of the two regions is 1:5. Suppose the area of this is A and the area of this is B. So what we are given is that A over B is 1/5. Right? That's the ratio. Or A is to B is 1:5. So immediately you got that B is equal to 5A. Because if you cross multiply B times 1, it's B equals 5A. So we can get B in terms of A. So actually we just got one unknown. That's what we've got. Because if I know what A is, then I have to multiply A by 5 to get B. Okay, so let's just hold on with that. Now, can we calculate what B is? What is this area? Well, we've got B here, but B is a trapezium, isn't it? B is the area of a trapezium. And there is a formula for the area of a trapezium. Right? All of you should know what the formula is. It's half the sum of the parallel sides times the height. Right, so there is a formula for the area of a trapezium. It's half the sum of the parallel sides times the height. Now, there's your trapezium here. This is trapezium because this is parallel to this. Oh, we already know that is 48. Right? Now we don't know the height. Let's give a name to the height. Let's call it C. So you got another unknown now. You got B and C and A. You got a lot of unknowns now, suddenly. But we have an equation, so let's see what we can do. Oh, so what is this? The area of the trapezium is half the sum of the parallel sides. So you got B, the height is C, so it's C into B plus 48. Height over 2. That is the area of the trapezium. Right, and that is the B that we've got, the capital B. All right, so looking a little bit complicated, but this is capital B. And what is A? A is the area of a triangle. And the area of a triangle is, it's a right angle triangle. And this is still C here. So it's half base. If you want to take the base to be C or A, it doesn't matter, but it's half A times C, half AC. So you've got B, that's the area of a trapezium, A, area of a triangle, and we know that B is equal to 5A. So what have we got? We've got the B B is this, C into B plus 48 over 2, that's B. That's equal to 5 this, I've just calculated this. So this is 5 times half AC. You can put 5 AC at the top and put 2 at the bottom. All right, then you cancel the 2's and the C's also cancel. The 2's cancel. And you're left with I've run out of space. So if you look at this, you got B plus 48 equals 5A. Right? I cancel the C's, cancel the 2's. Or if you like, I'm multiplying on both sides by 2. 2 goes away. But you got B plus 48 equals 5A. Right? But you got that A plus B is 48. We also know that A plus B is 48. See? So now you can say, I know what B is. B is 5A minus 48. You see, you can work B out in terms of A, small b. And then, so the B can be eliminated because in place of B, I can put 5A minus 48 if you bring it to the other side. Equals 48. And now I have an equation involving only A, right? Because I got A plus 5A is 6A. The minus 48 on this side, you bring the 48 to the other side, you get 96. 48 plus 48. So 6A is 96. And if you take 6A is equal to 96, and therefore you can calculate A. All right, it took a long time, but I'm sure there must have been some easier way of doing this thing. But as you can see, don't give up. You take the given information and although there are so many unknowns here, A, B, C, capital A, capital B, and so on, don't be afraid. Just use the given information, get the equations, and move towards your solution. Right? Substitute, cancel, substitute, right? Like the way we have done. And that is how you solve equations. But one important thing is that when you got something in terms of the others, you must replace that quantity by the other thing. So that thing is not there anymore. Right? The whole idea about having lots of unknowns is to reduce the unknowns. So you can reduce it by replacing B by 5A wherever you see them. That's what we've done here. And the same thing here, you can find B in terms of A here, because B, we take it to the other side. So wherever you see B, you only put A's. So B is gone. And that's what I did here towards the end. I got rid of the B. And then I had just exactly one unknown, and I could solve for it. Okay, so let's just get on to the next one. In the diagram, the outer semicircle has radius 2 centimeters. So you got a semicircle here. Its radius is 2. So let's just write down that information. The radius means the distance from the center to the boundary. So the radius of this. In fact, all these are 2, all the radii. Okay. And the inner semicircle has got radius 1. So this radius from here to here, so that's 1. Okay. Now, as soon as you got the radius of the circle, you can calculate everything. You can calculate its circumference, calculate its area, everything. You know the radius. So as far as these two circles are concerned, you can calculate all the areas. All the numbers are given. The radii are equally spaced. Oh, it means that these radii, they're all equal spaces here. Okay. Which means that all these areas are the same. This area is the same as that, because the radii are equally spaced. Now, what percentage of the entire shape is shaded? So the shaded part, and you got the entire shape, and we want to know what percentage of the entire shape is shaded. All right, now I'm going to write something down, but you must listen to me carefully. I need to know the percentage of the entire shape, right? So I need to know what maybe the ratio of this black part to the entire shape. If I know the ratio, then I can multiply that by 100 over 1, right? To get the percentage. Whenever you got a fraction, you can convert that to a percentage by multiplying by 100 over 1. So let's just work out the fraction of this shaded part to the entire shape. All right. It's easier to calculate the area of the entire shape. Okay, what is the area of the entire shape? It's the area of the half of the semicircle. That's the full shape. We know the area of a circle. So the area of a semicircle is going to be half the area of a circle, right? So I'm going to say half, or to work the ratio of the shaded part over the entire shape. The entire shape goes to the bottom. So it's going to be half of what? It's going to be half of the area of the semicircle. I'm sorry, half of the area of the full circle. The full circle has got area pi r squared. The area of a circle is pi r squared. Where r is the radius. So the circle itself has got radius 2. So pi r squared will be pi times 2 squared. So at the bottom, I've got the area of the full circle, and this is the area of the half circle, right? I'm not simplifying it, I'm just leaving it at the bottom. Now, what about the area of the top circle? Now, that's a little bit complicated. Not the shaded region. How can we work out the area of the shaded region? Well, what I can see is that this entire, if I add all these equal regions, then I got the area of this whole part here. Right? And this shaded part is 2/3 of the area, this one here. See, I'm tracing the area that we are going through. And I'm saying it's 2/3 because there are 4 equal areas here and there are 6 altogether. So the shaded area is 2/3 of the area of this ring. So we'll put down 2/3. Now, the area of the ring, if you take all this, it's equal to the area of the full semicircle, right? Which we already had. Okay, let's work out the area of the full circle. This is half 4 pi, so that's 2 pi. Pi times 4, and half of that is 2 pi. So the area of this part here, which I'm shading, And here, I have to remove from that area, this part here, to get the area of the point, the thing I'm pointing to. Right? I got the whole thing is 2 pi. So all we need to know the area of this part here. And this is the area of a semicircle, which is half the area of the circle. And the area of the circle here is pi r squared. And we saw that the r is 1. So the area of the circle here is pi times 1 squared, the full circle. But this is the area of a semicircle. I'm subtracting it because when I take this part here, the white part here, and take it away from the whole thing, I'm getting the area of what I call the ring, or the half ring. And then the area that I'm looking for is 2/3 of that half ring. And the ratio that we are looking for is 2/3 of that over the area of this. So that took a long time to explain. The rest of the things, you just have to simplify this thing, right? To get the fraction, what do you get? You get 2/3. Right, this pi times 1 squared is pi. 2 pi minus a half pi is 1.5 pi. At the bottom, you've got 4 pi divided by 2, so you got 2 pi, right? And this 3 is cancelled, the 2 is cancelled, the pi is cancelled. In the end, you get half. Very nice. The area of the shaded region is just half the area of the entire thing, and that is equal to 50%. Remember, the question was, what percentage of the entire shape is shaded? So a half is 50%. So that's the answer. All right, so you have to go in slowly. How do you calculate this area? Well, you say, well, it's part of this larger area, and I can calculate the larger area because it's the difference between 2 known areas, and then work the difference of the 2 known areas, and then see what fraction of this area that you're looking for. It's 2/3, and there we have it. Okay, so that's a rather tricky problem, but it can be done, as long as you do it slowly. The next problem, the faces of a fair die are numbered 1 to 6. When the die is rolled, one number will be face down, and the other 5 numbers will be visible. Okay, that's quite true. You get a die. We say dice, but dice is plural. One is die. Okay, so if you draw a die like that, and then there's got 6 numbers on it, and if these 6 numbers, when you throw this die, you have, goes down like this, and there is one number which is face down. When the die is rolled, one number will be face down. So there's a number which you can't see at the bottom, underneath. But all these 5 numbers are visible. Right. Okay. Now, the probability that 210 is divisible by all the 5 visible numbers is A over B. Now, what do you mean by that? We've got the visible numbers, the numbers on the die are 1, 2, 3, 4, 5, 6. All right. Now, they say the probability that 210 is divisible by all the numbers. Right. Now, which of these numbers go exactly into 210? Well, by all the visible numbers. So, which of these numbers are visible? 2 goes exactly into 210. So that's visible. 1 also, right? This is even, so 2 goes into it. 3 also goes into it. 3 times 70. But 4 doesn't go into it because 4 does not go into 10. 5 does, ends in 0, and 6 goes because both 2 and 3 go into it, so therefore 6 goes into it. So the probability that 210 is divisible by all 5 numbers, we can now see it, right? Because the visible numbers now are 1, 2, 3, 5, and 6. Those are the visible numbers. Right? And there are only 5 numbers which from the set which go into that. So those are the 5 visible numbers. So the number which you can't see is 4 at the bottom. Right? That's the invisible number. Okay. Now, if you read this thing again, the probability that 210 is visible by all the 5 numbers is that. So now the question is, when you throw a die, what is the probability that that die rests on 4? What are the chances that when you throw a die, the number 4 is at the bottom? The answer is quite clear, because there's only one time that number 4 goes into the bottom out of 6 possible choices, right? Because 1 could go at the bottom, 2 could go at the bottom, any one of 6 numbers. But if you want only 4 to go into that, the probability A or B, that's what they are saying, is divisible by all 5 numbers, is the same as saying that the probability that 4 is at the bottom, and that is equal to 1 over 6. That's the probability that 4 is the unseen one. Right, so that's the answer to that problem, but no, not yet. The value of A plus B, right? It's a simplified form. You have to say that, otherwise you could have 2 over 12, as we saw, 3 over 18. So this is a simplified form, and A plus B in the simplified form is 7. That is the question. Okay, so that takes care of problem number 22. So go on to problem number 24, 23 at least. A point inside a square is joined to the midpoint of each side as shown. So what we've got here is that there is some point inside and is joined to the midpoint. So in other words, these are equal of each side. It's joined to the midpoint of each side. So all these are equal. I'm using the same symbol because it's a square. So all the sides are equal. And therefore, the halves are also equal. So that's what you've got there. Now they tell you that the area of these funny shapes, this is 20, this area of this, the 3 areas are indicated. So this area of this quadrilateral, they tell you what these areas are. And they want to know, what is this area? And very interesting problem. And it can be solved if you know the following fact. There's only one thing that you need to know. And it is the following. It's a very simple statement. If you got any triangle, and if you got the midpoint here, you join a vertex to the midpoint, then these 2 areas are the same. The area of this is the same as the area of that. The reason is quite clear because when you're calculating the area, it is half this multiplied by the height of the triangle. When you're calculating this area, it's half this times the height of the triangle. Now this triangle here has got the same height as that, because to draw the height, you have to take this common vertex, you draw a perpendicular. So this triangle has got this as a height, that triangle got the same height. So they got the same base and the same height. Therefore, they must have the same area. So these two areas will be the same. Whenever you are joining a midpoint, the areas are the same, right? That information can be used very effectively to solve this problem. It's a very nice problem, and you'll see now why. So you can see what I've done here is this is my original picture, and this is the midpoint. I've taken the center and I've joined it to the four vertices with the red lines. These are constructions. The original picture had this. It did not have that point joined to the four vertices. I'm joining those four in order to solve my problem. Now, why does it solve the problem? The reason is this is the midpoint here. So therefore, these two areas are the same. I'm calling these two areas A. I'm calling these two areas B for the same reason. I'm calling these two the areas C, and I'm calling these two areas D. Right? So we need to calculate this area here. Now watch. It's the same picture, but without the red lines. Right? I'm going to write on the following: 20 plus the unknown area is equal to what? Well, 20 plus the unknown area is equal to those two, A plus B plus C plus D. If you write it in terms of A, B, and C, and D. So it's A plus B plus C plus D. Now watch. These two, this is the same as, you got A plus B, A, D, B, C here. So if I rearrange these, I can say this is the A plus D plus B plus C. If I put the A and D together, the B and C together, but I know what A and D together are. This is 32. And if you put B and C together, I know what that is. That is 16. B plus C. So there it is. You got a very simple equation, right? 20 plus the unknown area is 32 plus 16. So therefore, the unknown area is 32 plus 16. 32 plus 16 minus 20, which gives you 56, 36. Very interesting that this area plus this area is always this area plus this area. You know what happened here? It's 48 minus 28. The answer is 28. This area, the sum of these two areas is equal to the sum of these two areas. That's not very clear, but when you do it like this, you can see the sum of these two areas is the same as the sum of these two areas. That is because of the way, because of the median. You call this the median of a triangle. The line that joins the midpoint of the opposite side is called a median. A median bisects the area of a triangle. That is what I wrote earlier, that the median bisects the area. So these two areas are the same. Bisects the area. There are three medians, and you can take any median and the same thing will happen. Why are there three medians? Because every triangle has got three vertices. So therefore you can draw three. Okay, we are at now problem number 24. And it's 6:05. So maybe we can stop there. I usually abuse your time, but it'll be a nice place to stop so that you can try to work out the last two problems to see how good you are now. Okay, you got a problem involving distance and time here. Right? Motorcycle from home to the beach and so on and so forth. And the last problem, right, this is another interesting problem involving medians and means. Mean means the average of several numbers, and median is the middle number, right? When you do statistics, you know what median is. I don't know whether you guys are doing statistics these days, but median is a middle number of a collection of numbers. So if you had numbers like, if you write 17, 19, 25, 93, 106, 220, and 500. So write them in ascending order, then the middle number, right? 3 on this side, 3 on this side, that is called the median. So it's easy to know what you mean by median, easy to know what you mean by the mean, and this problem only requires you to know what the mean and the median mean. A very interesting problem, right? Knowing very, very limited knowledge is required, pre-knowledge, but given a certain, this problem here, they ask you to calculate the value of an unknown quantity, and it'll be very interesting to see whether you can do it. Okay, I'm going to leave you with those two problems. Next week, we will do those problems together with, we'll go back to 2020, because that one we haven't tackled. We'll do these two problems, and we'll go as far as we possibly can with 2020, because next week is the last week altogether. If you want, I can go do the whole lot, but it'll take you, you'll have to go all the way up to 7 o'clock or more. Okay, but I need to say that 2020 is quite hard. I told you, I will explain to you why I jumped to 21. But 2020 was quite a difficult year. That was the first year of COVID, if you remember. And normally they have 3 rounds. In that year, they had only 2 rounds. And I think even last year they had 2 rounds, I can't remember. And because there were 2 rounds, the second round was very difficult because there were only 2 rounds and the top 10 in the country were chosen from those 2 rounds. So they made that paper quite hard. All right, so I've sort of skipped that, and maybe next week we'll do, those ones which look, we won't do the problem which look insane. We'll just do those which don't kill your confidence. Okay, so I'm going to stop sharing at this time. I'm going to stop the recording as well.
And there you have it. Another insightful Olympiad training session with Professor Pile. Remember, practice makes perfect.